Hello, here is our next thermochemistry aspect of AP chemistry, looking at heats of formation. Um, so, formation reactions, pretty straightforward, are any reaction that's written with elements in their standard states to form 1 mole of a pure compound. So when you're looking at reactions, the reactants can only be elements from the periodic table in their standard states, meaning you have to know solid, liquid, or gas. And the compound that it forms as a product can only have a coefficient of 1. That is an only and always thing. If you're not sure about standard states, obviously you can look at the appendix in your book, as well as reference sheets that are on my website. But remember that because enthalpy is a state function, the delta H of formation of any element in its elemental state is 0 because they are found naturally. As we said, the definition that it requires 1 mole of compound or product to be made, the coefficients can be anything for the reactants, fractions, whole numbers, things of that nature. Writing reactions, formation reactions. So we'll start with the formation of carbon monoxide. The formation reaction is a reaction between elements in the compound. So we know it's carbon monoxide. So we know we need carbon and oxygen. So there's your carbon and oxygen gives you carbon dioxide gas. Pretty straightforward. The elements must be in their standard state. So how they are formed naturally on the planet. Since there are several forms of carbon, but the only one with a delta H of 0 is graphite. Diamond does not have a delta H of formation of 0. That's why it's graphite. Oxygen, we know, is a diatomic gas. Nothing new there. So we rewrite our equation to show carbon as a solid in the form of graphite and oxygen as a gas. Obviously, all equations must be balanced, and we know the coefficient of the product compound has to be 1, so you can't get around that one. So use whatever coefficient you want to make everything else work out so that it's balanced overall. So we have carbon as graphite, and half of your oxygen gives you carbon dioxide as a gas. Again, notice the product only has the coefficient of 1. We don't write ones. Elements on the reactant side are in their elemental state with the correct state. That was redundant. Yay for me. And then coefficients to make everything kind of work out in the end. Now, once we have a reaction, obviously we got to figure out the delta H of an overall reaction from different compounds that are made from their individual elements. So any reaction can be written as the sum of formation reactions, or the reverse of formation reactions, for the total reactants and products. So delta H for a reaction is then the sum of delta H of formations for the component reactions. So looking at an overall reaction versus each individual piece of the overall reaction. So we have this equation, which is on the equation sheet for the class, where delta H of the overall reaction is the sum of the heats of formation of products minus the sum of the heats of formation of reactants. You guys know the sum sign, and n is just the coefficient. Pretty straightforward. So here's a reaction of the combustion of methane. We have individual reactions in the diagram showing of the decomposition of methane, the formation of carbon dioxide, the formation of water. So one way you can look at it is all three of these reactions, or for our purposes here, we're going to look at it as heat of formation. So in the equation, formation of carbon dioxide plus 2 times the formation of water, looking at our products, minus the heat of formation of methane plus 2 times the formation of oxygen are reactants. Plug all your numbers in. Notice in the white that our oxygen has 0 delta H of formation. Elements in their standard states have a delta H of formation of 0. Do the math, and minus 802.5 kilojoules matches the diagram that's in purple. So we know that works out. Yay. Here's the overall reaction that I know to have that delta H. So if you're trying to solve for the delta H of an overall process, if you know formation values, you just do products minus reactants. Quick heads up, most things in thermodynamics are products minus reactants. When it comes to bond energy calculations, which are very similar to this, is reactants minus products. So it's the reverse. Most things in chemistry are going to be products minus reactants, but bond energy calculations are reactant minus products. We'll get to that a little bit later. So here we go. Same thing we just saw, just looking at it from a different perspective. Let's say you were looking up data in the appendix. You would get this information, plug it in, and you get your answer, which interestingly enough doesn't match my previous slide. Who knows why, but the work is what matters. A lot of the stuff I'm going to be looking at when it comes to assignments, assessments, whatever we're doing in class this year is, can you set the problem up? Most, if not everything, from a homework perspective, I have answers provided, and sometimes there's work provided with it. But at the end of the day, if you can't set the problem up, you know you'll never get the answer right. You know, a mathematical error, when it's set up correctly, you can fix that. A typo, when you set it up correctly, or not typo, typing it in the calculator incorrectly, you can fix that. But if you can't set it up correctly, you're never going to get it right in the first place. So here's a problem. Let's pause the video and try this on your own. All right, we are back. Ethanol is used as an additive for many fuels today. What is the delta H for the combustion of ethanol? On the right, it gives you your heat of formation values. Answer should be E. Are there any questions? Okay, moving on. Again, products minus reactants. The biggest thing is not to mess up your algebraic signs. The biggest, most common mistake that most students make when they're doing heat of formation reactions and calculations is it's products minus reactants, but then each individual value that you're using can be either positive or negative. So got to keep track of your algebraic signs. Biggest mistake you're going to make is by not distributing the negative sign. All right, everything after this slide is kind of extra stuff that is not part of the class, but I included it here just to have it. You can look at it on your own. I'll go through it, but I'm not going to be explaining anything. If you have any questions on this other extra stuff, please email me and we can talk about it. Thank you. I guess quickly, the concept of work is not included in the class. It's beyond the scope of the class, so you will never be assessed on it or it'll never show up. So that's what this stuff is looking at.